The central processing unit, or CPU, is often called the brain of the computer. It's the most critical component responsible for processing all instructions that make a computer function. The CPU consists of two main components. First is the control unit. The control unit manages the flow of data and directs the operations of the computer by telling other components what to do. The second main component is the arithmetic logic unit, or ALU. The ALU performs all mathematical calculations and logical operations, such as addition, subtraction, and logical comparisons. These two components work together, constantly exchanging data and instructions. At the heart of every CPU are transistors, the fundamental building blocks of modern processors. Transistors act as tiny electronic switches that can be turned on or off to represent binary data, the ones and zeros that computers understand. Modern CPUs contain billions of these microscopic transistors, allowing for incredibly complex calculations and operations. The CPU operates based on a clock that sets the pace for all its operations. This clock generates a series of electrical pulses that synchronize all the CPU's internal components. The clock speed, measured in gigahertz or gigahertz, determines how many instructions the CPU can process per second. For example, a CPU with a clock speed of 3.5 gigahertz can perform 3.5 billion cycles every second, with each cycle potentially executing one or more instructions. Modern processors can execute billions of instructions per second, allowing computers to perform complex tasks almost instantaneously. Computers interact with the outside world through input-output operations, also known as I/O. These operations create a bridge between humans and machines, allowing us to communicate with computers. Input operations convert human actions into electrical signals that computers can process. Output operations convert the computer's digital signals back into forms that humans can understand. Input devices are essential components that convert human actions into data the computer can understand. Keyboards transform key presses into character codes that computers interpret as text input. Mice translate physical movement into cursor position coordinates on the screen. Touchscreens detect the position and pressure of finger touches, allowing direct interaction. Microphones convert sound waves into electrical signals for voice commands or audio recording. Output devices take the computer's digital signals and convert them into forms humans can understand. Monitors display visual information by illuminating thousands of tiny pixels based on the computer's instructions. Speakers convert digital audio signals into physical sound waves that we can hear. Printers create physical copies of digital documents by applying ink or toner to paper. The CPU coordinates all input and output operations through specialized hardware called I/O controllers. These controllers act as intermediaries between the CPU and various input and output devices. Input controllers manage devices like keyboards and mice, handling the conversion of external signals into data the CPU can process. Output controllers handle devices like monitors and printers, converting the CPU's digital instructions into appropriate output signals. I/O controllers perform several critical functions that make communication between devices and the CPU more efficient. This controlled data flow allows for seamless interaction between users and machines, making complex computing operations accessible to humans. Let's put everything together to see the complete input-output cycle in action. The cycle begins when a human interacts with an input device, like pressing a key on a keyboard. The input signal travels through the input controller, which converts it into a format the CPU can understand. The CPU processes the input and generates appropriate output data. The output data passes through the output controller to the appropriate output device, like a monitor. Finally, the output device presents the information in a form the human can understand, completing the I/O cycle. This continuous cycle of input and output operations allows for seamless interaction between humans and computers. Software execution begins when a program is loaded from storage into RAM. When you run a program, it's copied from storage to RAM, where it can be accessed much more quickly by the CPU. Once in RAM, program execution is managed by the CPU through what's known as the fetch, decode, execute, store cycle. First, the CPU fetches an instruction from RAM. Next, it decodes the instruction to determine what operation to perform. Then it executes the instruction performing the actual operation. Finally, it stores the result in memory or CPU registers, completing the cycle. This fetch, decode, execute, store cycle happens billions of times per second in modern CPUs. Programs are written in high-level languages like Python or Java, which are human-readable but not directly understood by the CPU. Before execution, this code must be translated into machine code, binary instructions that the CPU can directly process. This translation can happen through compilation or interpretation. A compiler translates the entire program at once, creating an executable file that can be run multiple times without retranslation. An interpreter, on the other hand, translates and executes the code line by line in real time, which is more flexible but typically slower. Whether compiled or interpreted, the CPU ultimately executes binary instructions, the only language it truly understands. Modern computers connect to networks and the internet through network interface cards, or NICs. Networks rely on various protocols, standardized rules that govern how data is transmitted between devices. Common protocols include HTTP for web browsing, TCP/IP for data transmission, and DNS for domain name resolution. Let's follow the journey of a web request to understand how internet connectivity works. When you browse a website, your request travels through multiple network components. Step 1. When you type a URL like example.com, your computer needs to find its IP address. Your computer sends a DNS query to a DNS server, which translates the domain name to an IP address. Step 2. With the IP address, your computer sends an HTTP request through your router to the internet. Step 3. The web server receives and processes your request. Step 4. The server sends the requested data back through the same network infrastructure. Finally, your computer processes the response data and renders the website on your screen. This process happens in milliseconds, connecting you to websites and services across the globe.